Thank you, Denise, for that introduction. And I just want to say it's an honor to be a part of this event today, and quite humbling, actually, to be honest with you, to follow a very esteemed roster of presenters so far this afternoon. So I'm very excited to be talking to you all today about what I think is one of the most important topics in AI, but especially for trust in AI, and that's about security, and in particular security in the face of adversarial attacks and adversarial AI, as Dr. Horvitz actually just touched upon in the last talk. As we get started here with the presentation, I just want to highlight the potential that AI has to offer for the DoD, for the nation's interests itself. And we've talked about this, as the larger theme for today is why AI? What's important about AI? Where can we use AI? And we've seen all of these possibilities throughout the various briefers today. And really comes down to augmenting the performance and the capabilities of the human teammate, really, right? Partner, not just a human as an operator of AI and ML, but as the teammate for the system. From the cases that Dr. Horvitz just so eloquently talked about in the last brief, for using it for medical purposes to augment, very highly skilled, high expertise pathologists to enable them to identify certain forms of cancer and reduce the errors where humans are already outperforming the AI. But they can reduce errors by utilizing these systems for humanitarian aid and disaster recovery, where time is of the essence, right? Quickly responding to disasters and identifying where needs are, over large areas, and where scale is just beyond the human, maybe the capability of a human to quickly identify those areas. To the autonomous vehicles that we've heard much about, right, where there's potential to save, thousands or hundreds of thousands of lives by adopting autonomous vehicle technology. But there's this overarching, this goal that the AI can meet, the needs where scale and efficiency is just, far superior to human capability. Next slide, please. To put that into a military context, right, from the DoD perspective, if we're looking at situational awareness type applications, looking at a large area, and trying to get a handle of what's happening on the ground, we've got hundreds or thousands of objects that an analyst needs to quickly identify, and can't spend the time or the attention. And Dr. Mayberry, pointed this out with how much overload really is on our analysts to handle this information. AI is perfectly matched for doing those tasks so that the analyst can actually use the gray matter to make sense of what they see. Or to kind of go back to the prior slide where I talked about identifying certain forms of cancer, right? SAR, synthetic aperture radar, applications where there's a high degree of domain expertise, right? That image that we show of a processed imagery, there's a high degree of domain expertise and experience that's required to be able to look at that image and know that it's a bulldozer. And again, so this is really about where AI can provide or augment humans where the scale and the efficiency is just unmatched. Next slide, please. However, with this potential, there's certainly problems to be faced and threats to being able to utilize this, at a larger scale. And really, this area is known primarily as adversarial AI or adversarial machine learning. And it goes back several years, and there's been an intense focus on this area in the research community, which is great to see, because this is the kind of research we need to enable trusted AI. From that, one of the earliest papers on this topic, where we take this, this image of a panda, add subtle noise. It looks like random noise, but it's not random noise. Those are carefully chosen pixels with the right perturbations at the right places that change the classification of the machine learning algorithm to a given, but also not just changing the classification, but also doing it with high confidence. So this AI ML capability now is wrong and very confidently wrong, in fact. And you can see how this can be utilized in other ways, right? So the center there, we show how this can be replicated in the physical domain, where adding a few pieces of tape to a stop sign significantly changes what the classifier and perhaps a self-driving car sees. In this case, to a 45-mile-an-hour speed limit sign. To the left of that, right, a different version of this same type of attack. We put a couple bumper stickers on there. And in this object detection application, the stop sign isn't even recognized as being in the scene. So I leave it to others to decide which is the worst case, whether the car doesn't see a stop sign or whether it sees some speed limit type of sign. But the point is very subtle, mostly imperceptible, additions to the scene are drastic in terms of how they're perceived by the machine learning. And then our final example here is just to show that we can realize this in other subtle non-random ways. Taking for example this 3D printed turtle where the pattern that's been laid on the shell of the turtle looks natural in many ways, but from any angle, from any rotation, it's again causing serious misclassification in the AI ML models. Next slide, please. And so to bring that back to the DoD or Air Force perspective, I go back to that SAR example where I'm classifying this initial image as a bulldozer. In the middle there, I've added that subtle non-random noise, right? Picking the right pixels at the right places and at the right intensities, and adding that back in still looks like noise in that SAR image, but again, drastically changes the classification. And so the takeaway from all of this is that the AI is vulnerable to non-random and imperceptible perturbations, which we need to tackle before we can really have full trust in this capability. Next slide, please. So I would argue that trust is established through reliable and repeated accurate performance. So whether that's human to human or human machine, right? If I have a human colleague, I'm going to trust them if they're reliable. If they repeatedly show me that they're going to do the things that I expect them to do or that I would do myself. And the same goes when you make that partnership between a human and a machine, right? The machine has to repeat the actions in a reliable way and be match in a lot of ways what the human analyst or human operator or human teammate, I guess we're saying, what they expect to see. And others have touched on these next two points, but there's other factors that are a concern in this relationship, right? There's a concern certainly of automation bias, where a human realizing that the AI is there as a partner pushes too much of the decision making off to the machine. And relies too much and trusts too much in the system and does not act as a double check. And I think we've all heard these reports, right, of the self-driving cars where, although you're sitting in the driver's seat, the people kind of tend to leave all the driving to the autopilot and zone out, and where that's can have catastrophic effects, right? On the other hand, we have the case where the human just believes in self so much. Has little to no faith or trust in the AI system and discards any recommendations or any of the outputs from that, and they call that illusory superiority, right? So we kind of just lose the advantage of what the AI ML technology can provide for us by just believing that me as the human knows all the answers, and so. To bring that into the context of adversarial AI, these adversarial attacks that I showed in the prior slides, they break that implicit trust between the human and machine. They cause the machine to fail in ways that a human would not. If you look back on any of those examples, right, what you saw, you would not change as a human observer or analyst looking at those. You would not change your decision, your output from that process. But the machine, in all those cases, the machine does. And so we need to understand why those vulnerabilities are there, and in order to maintain that trustworthiness, we need to apply various security principles. Next. So here's a very simplistic view of the machine learning pipeline or AI development pipeline, right? Two processes basically: the training phase and then the inference phase. It's a matter of collecting data, labeling that data, getting some sort of understood truth to that, and then training up our model, and then we deploy that against new data and use that to infer or classify. So this is a very, very simple supervised learning type of example. If you can click forward, please, to build the slide, just to show what the vulnerabilities are in this pipeline, right? So I've already shown you what adversarial samples, right? Those inputs to the inference phase, where an adversary has manipulated the data in some way in order to evade the classification of the detection process. Next, please. There's also other attacks across this pipeline, right? So I could do very similar things to manipulate the data that's used for training, change labels, perhaps, in order to degrade the learning process, right? Make it so that it's a slower process, or that you don't converge on a model that's accurate to the degree that you desire. Next. There's also the possibility that I could add certain samples in that don't affect the training for most cases, that you learn properly, in most scenarios, but for very select number of inputs at inference time, I've got a backdoor Trojan where if I give it a specific pattern or sample at test time only, you'll cause misclassification. So the model performs as expected in any other case, except for that these few small scenarios where I've got a backdoor. Next, please. And then depending on the way this model is deployed, right? If there's some sort of public-facing inference capability where you can an adversary can query the model, right? I could throw a number of samples at it and determine outputs, and maybe learn a surrogate for your model, and kind of extract information about the model that you've spent years, maybe millions of dollars to develop, and take away an advantage in that space. Next. And then, as a privacy concern, I can do very similar attack and again, query and learn something about the training data that's been used to develop that model, and maybe steal some information through that model inversion type of technique. Next slide, please. So really, yeah. So the point of this is that securing against these types of attacks requires mitigation at all stages. And these threats, if you want to look at it from a cybersecurity or information security perspective, the various elements of the Parkerian hexad, confidentiality, integrity, availability, possession of control, or authenticity and utility, we can categorize many of those threats that I just pointed out in the prior chart along this same way. So go ahead and build the next 6 go right ahead, and just to kind of highlight those points I touched on just in the prior slide. Confidentiality, can be threatened through model inversion, right? Stealing private data in our training set. The integrity of our model can be compromised through those backdoors, the backdoor Trojan attacks that are inserted into the training data set. The availability, or the ability of our system to operate in spite of attempts to degrade it, is compromised by data poisoning, right? I talked about how that could cause the model to not learn, or to learn slowly. That's certainly a concern. Again, having control of your model, possession of the model, if there's very unique characteristics of that you don't want an adversary, a competitor, whomever to have. If there's ways to extract that through black box querying, that's certainly a concern as well. The authenticity can be attacked by those adversarial examples we talked a lot about. And then the final one is utility, right? So techniques that we could use to ensure many of these other elements are still secure. For example, privacy. Techniques such as differential privacy can be threatened through things like false data injection, where an adversary has control of one node perhaps and can feed you false data back into it that disrupts the learning process under that scenario. And in many ways, some of these threats can fit under multiple elements for sure. Next slide, please. And so the key, in terms of developing security around this whole pipeline of development is to have a reasonable and accurate model of the adversary in order to develop your strong defenses and mitigations. And what I mean by that is whether it's in defense or whether it's in business, there's always somebody who's looking to compromise the situation and looking to cut corners and steal, the intellectual property or the knowledge that you've spent, long hours developing. And how and where they can do that depends on their knowledge of your system, the knowledge of the techniques and the models and algorithms that you're using. What the capabilities they have, what access to your system do they have? Can they actually directly access your data, or do they only have access to physical aspects of the system? As I mentioned in the stop sign example, right? If I can only do things in the physical realm, I need to actually capture that as part of my adversary model. And then finally, what are their goals? What are they trying to do? Are they trying to just disrupt the process? In some way, degrade the trust that the analyst or the human teammate has in the system, or are they really just trying to evade a detection from those types of systems? And other things to consider, when developing this strong adversary model, is that attacks are often cheaper and faster to generate than defenses, right? So we spend lots of time and energy on these applications. And we need to make sure that they can't be easily thwarted or undermined with a very simple $2 attack, tape on a stop sign type of thing, right? You also need to understand that the attack success rate does not have to be better than your defense success rate, or in fact, it doesn't need to be high at all. In some cases, in certain areas, perhaps in defense applications, there's a possibility that one attack is catastrophic, and one successful attack against this capability is catastrophic, and we need to ensure that we're developing ways to not allow that to happen. And then finally, I think this mostly goes without saying in certain contexts, but you cannot assume the adversary is going to play fair, right? We cannot, think that they're going to play by a set of rules that we may hold ourselves to, and so that has to be captured again as part of our adversary model that we're developing against. Next slide, please. So the one way that we're thinking about attacking this problem really is adopting from some of the cybersecurity mindset, and they're really looking at separating out the development of defensive measures from certain types of attacks, and a kind of a red teaming approach, right? So the red team really focusing on what are those plausible or credible attack vectors that could be employed against these applications that we want to develop. And again, it goes back to that developing a really rich sense of the adversary model, and then allowing our Blue Force team in this case to really focus on novel algorithms and processing that enable us to do the things that we want to do in the timelines that we have, and the constraints that we have, but are agnostic to the defense or the attacks that may be faced. And so we're not constantly, patching holes against certain attacks, right? Largely, research tends to focus on mitigating against specific attacks. We want to be more broad in our coverage and make sure that we are robust and resilient to all those types of attacks. And that's a very important key to our strategy. And then, adding into that, ways of measuring and evaluating the effectiveness of those defenses, and new ways of evaluating that, and also bringing human analyst, human operator, human teammate into the process, whether they're in the loop or on the loop, and in studying the effects of human-machine trust, but also what are the risks and what are the what potential vulnerabilities can be added or mitigated by introducing humans into this process. Next slide, please. So lest you think that, with a heavy focus on, in particular image classification problems and supervised learning in general, I don't want to leave you with the impression that, this is only a problem in the supervised learning space, right? This is adversarial AI is a problem across all of AI. And so, this example I like to show here is really fascinating to show, how adversarial AI can be used to attack deep reinforcement learning. So this very simple game, from the folks out at Berkeley, called "You Shall Not Pass," where the blue player is trying to get past the red player and across the finish line without being stopped. And under normal policies, the blue player wins over half the time. And when we change the game, and again, now the red team is no longer playing by any set of rules. The red player learns this adversarial approach to just drop to the ground, crumble down to the ground, really just confuses the blue player. And then now they win 80% of the time. So, understanding that adversarial attacks are not limited to supervised learning is really important to, cover trust in AI as we expand the scope and breadth of AI development. Next slide, please. So in closing, as we go forward, I believe that a multifaceted approach is necessary to address the security of AI so that we can truly establish that bidirectional trust between human and machine. The multifaceted approach is necessary because we won't solve this only through more AI. We can't just add more AI and algorithms and models that will solve the problem. We need to look at it from a very holistic approach. And we also need to emphasize mitigations rather than solutions, because we really truly need robust and resilient AI. We need to be able to, we have to understand that we're going to be operating with an adversary, as part of the game, right? And so being resilient to those actions, being able to recover quickly and get back to operating is important, but also being able to operate through those types of attacks is certainly important. So I outlined, kind of adopting that cybersecurity mindset, and I believe that's a strong approach to envision the types of attacks we could face and the threats to the AI applications that we need to develop. And one way to do that is to engage with the non-traditional communities, not the non-AI ML communities. So the black hat types of groups that will help us to identify early, ahead of our adversaries, what those novel threats are and help to accelerate the research in that space. And then finally, as Dr. Horvitz just mentioned in his chart, looking at new measures of performance, right? Accuracy is great. Everyone likes to tout their accuracy on a problem, but what does that really mean when we want to talk about trust and security? And so, coming up with new measures of performance and effectiveness are certainly important. So I just want to end by saying security must be a critical design characteristic for all future ML development. By the time we look to deploy these systems, if we're trying to add on security at the end, it's probably too late, and that's a lesson we can learn from past efforts. So think with a security mindset from the beginning. Understand where the adversary can place themselves in your process, in the whole pipeline from beginning to end, and design with those things in mind, and that will really go a long way towards developing that human-machine trust. So next slide. Just with that, I'd like to say thank you for your time and attention. It's a pleasure to be a part of this event, and I look forward to the next couple of days, listening in on all the great presentations, and for many years to come with this very important topic. Thank you.